Okay, good. So for today, we're gonna talk about limits and continuity. As I told you last time that everyone, if you remember when you learn calculus 1, you have limit here and you used to look at the left hand limit and the right hand limit. And if the left hand limit and the right hand limit, they are equal to each other, you're going to conclude that the limit exists. And finally, you're going to conclude that, hey, that limit is also equal to L, which is the value of the left hand limit and the right hand limit. Today, we're going to extend the idea to two dimensions or function two variables. The good thing is that we're going to keep everything that we learned in Cal 1 and we're going to repeat it again in two dimensions. So let's start by looking at the notation. So this is the notation of limit in two dimension. So you can see that the different thing is that now we are looking at function of two variables. So the function gonna be f, x, y. So you're gonna use two inputs here, which is x and y, which means you need to write more on the convergence notation here. The convergence notation gonna be a point xy approaches AB. So before you have x approach A, but now you're gonna need a pair xy going to AB, which is fine. Well, because it's in two dimensions, so you need that one. And the limit gonna be L. The notation that we use gonna be L anyway, because the limit gonna send function to a real number. So the range here gonna be just the L, the real number, as the concept as in calculus 1. So to compute limit here, what are you trying to compute? Is you trying to compute the behavior of fxy where xy goes to AB. Basically, you have to think in your head that what are you trying to compute is you have a plane xy and you're trying to compute the limit of fxy where xy approach the point AB here. So you want to know that when xy approach AB, so what is the limit of the function? So keep in mind that you could have more than one way to get to the point AB. It is not just left hand and right hand like in calculus 1. Does it make sense? So first of all, we're gonna repeat the theorem that we learned in Cal 1. And I will tell you now that everything that you learned in calculus 1 still hold in calculus 2 in two dimension, which means if you compute the limit of constant, you still get constant. If you compute limit of a function x, you're gonna have just a because x go to a. So limit of x gonna be a. Limit of y gonna be b because xy go to ab. Does it make sense? Well, compared to what you learned in Cal 1, you used to have limit of x where x go to a. Well, this is just a in Cal 1, right? Because seem like you can plug in number a here because of the continuity of the function fx equal to x. So you're gonna plug in a here, you get a. Well, we're gonna keep this result in two dimension. It's still okay to use it. It's still okay, but if you are looking at y now, so it's gonna be b because y approach b. Well, this is fine, easy one. So which means when you use it in the problem, if you see x and y, it is okay if you plug in a and b into x and y, fine. As long as you can compute it, fine. Okay. Also, you have a lot of theorem in Cal 1. You can use it into variable case as well. So let's look at this one. So if you have limit fxy equal to L, limit gxy equal to m. If you add them up, the limit of the sum here gonna be just L plus m. Well, very simple, similar to what you learned in Cal 1. Yes, because if you have limit of f equal to 5, limit of g equal to 6, limit of f plus g should be 11. Well, easy. And limit of f minus g should be -1. Yeah, it must be something like that because, well, it is similar to what we learned in Cal 1 before. The notation just changed from x go to a to xy go to ab. But the result is similar. And if you have constant c here, you can pull out, fine, and then you get c times that limit. If you have the product, yes, you can multiply L and M together, fine. If you have the quotient, you can do L over M, good, easy. If you have F to the n power, it's just L to the n. This slide, we're gonna conclude that all basic computation that we learned in Cal 1 still good for Cal 2. And you can use this thing when you compute the limits. Let's look at the example. For example, let's try to do example 3 together here. I have limit of 10xy minus 2y squared over x squared plus y squared, where xy go to 1 and -1. What I can do here is, well, similar to Cal 1, why don't we plug in x and y? We can. So it's gonna be 10 times 1 times -1 minus 2 times -1 square here, and then over 1 square plus -1 square. Well, this is valid by just plugging in x equal to 1, y equal to -1. It's okay to do that. This is okay because you have theorem that you can plug in x by a, where x go to a, and you can plug in y, where xy go to ab. You're gonna get b. And then also you have all limit theorem here, which means if you see the quotient, you can break it up and do limit for each part. Or if you have some difference, or you have constant, it's fine to do the same thing as you did in Cal 1. So which means I have the quotient here, I can split it. And I compute numerator first, I compute denominator after, and then after that you take limit inside, and then you use the limit of sum, limit of difference. Well, everything gonna be okay to do it. And then once you compute this thing, well, this is the easy one. So -10 minus 2 over, well, be careful about the negative sign. And then that is 1 plus 1, and then that is -12 over 2, and that is -6. Well, this is the very simple example and easy one. So you can see, you can plug in everything and good, fine, you get -6. This is the basic one. Does it make sense? Everyone are good? All right, so we're gonna move to another complicated example. So let's take step to more harder example. So let's start by looking at example 3.2. Well, let's try to do the plug-in concept first. So every time when you see the limit function, the first thing that you should do is you're trying to plug in x, y into this thing first. If it is computable, good, you're gonna get that answer. -6 is the example here, and then you're done with that question. Well, let's see. If I try to plug in this one, I'm gonna get 2 square minus 4, and then x is 2, y 2, and then 2, and then x approach 2. Yeah. So this is going to be 4 minus 4 over 4 minus 4, which is going to be 0 over 0. Bam. This is the same thing in calculus 1. Most of the time, the tricky part of computing the limit is you're gonna get 0 over 0. And in calculus, 0 over 0 is indeterminate form. As we learned in calculus 1, that this is not okay to answer 0, or this is not okay to answer undefined or something. This is indeterminate form, IF, which means you need to simplify or do something first before you compute limit, because this is not computable. Zero over zero can be anything, right? Can be 1, can be 2, can be 1/2, can be undefined, can be infinity, can be 0, can be -1. This can be any number, because 0 over 0 means you trying to look for the number that multiplies 0 and get 0. Well, 1 is that answer too, because 0 times 1 you get 0. 1/2 is the answer too, because 0 times 1/2 you get 0. So 0 over 0 can be anything, because any number gonna multiply 0 and then you get back 0. Well, this is the problem called indeterminate form in Cal 1. And what you learn in Cal 1, what would you do in Cal 1? So let's do a recall. What would you do in Cal 1 if you face 0 over 0? Some of you are gonna say, hey, Ajahn Kap, when we learn with Ajahn Ratinan, we used to do factoring. Yes, that is the one way you can do it. If you can factor, well, do it. Good. Or some people are gonna say, Ajahn, we used to do the conjugate. Well, we can multiply the given limit by its conjugate, and it's going to reduce to the form that we can compute it. Yeah, fine, you can do conjugate. Or some of you are going to say, Ajahn, in Cal 1 we also do the something called L'Hopital rule. Why don't you differentiate the top one, differentiate the bottom one, and you're going to compute limit easily by using the L'Hopital rule. This one is questionable now. Can we use it? Well, there's no L'Hopital rule into dimension. Well, maybe there is, but we have not touched that part yet. So let's throw away the L'Hopital rule. This is not going to be in your head for 2 dimension, because, well, before using the L'Hopital rule, you need to learn what differentiation into dimension first, because you need to differentiate something, right? It's confusing now to talk about differentiation, because we are now learning limits now. So let's keep it simple by looking at 2 techniques first, factoring or conjugate. So if you see 0 over 0, my recommendation is do the factoring or do the conjugation. This is 2 ways that you can do. Let's see for this example, limit xy go to 2, 2. Okay, everyone get ready. Y minus 2, y square minus 4, sorry, over xy minus 2x. Let's do the factoring. It seems like you can factor it out, because on the top one, you have y square minus 4. This should be good to factoring. Everyone knows since high school that you can do y plus 2 or y minus 2. If you feel like this factoring is way too hard for you, you are in trouble. This is not that hard at all to factoring this thing. So if you feel like this is uncomfortable to you, you need to review your algebra, because this is going to be the one that we use a lot. So when you multiply a plus b and a minus b, so it should be a square minus b square. And this thing we're going to ask you a lot to factor. So make sure you know how to factor this thing. And then after that one, xy minus 2x on the denominator. Well, you see the factoring, because I can see x. I'm going to pull out x. So I have y minus 2 here. All right, lucky. Y minus 2 cancel out. And then at the end of the wall here, you're going to have y plus 2 on the top, which is 2 plus 2. And then on the bottom, you have x, which is 2. And that is 4 over 2, and that is 2. Well, now this is good. Well, you can see it is computable now after you cancel out y minus 2. So on your practice problem this week and on the exam, maybe you're going to see the question like this. So it requires you to factor something and cancel out so you can compute the limit. This is the same concept as you learn in Cal 1. But the different thing is that now you are working with x and y in the function. Does it make sense? The concept is the same to me. I mean, hopefully to you too, that you need to factor and compute the limit. Well, I will tell you here that because we are learning calculus, I'm not going to put super hard factoring for you. All you need to know is you need to know a square minus b square. When you factor it, you get this thing. Whoa, this is important. And also, if you have a square plus 2ab plus b square, you need to know that this is a plus b square. If you can factor it out, you know, like x minus a times x minus b, if you factor it and then you get x square minus 2ab x plus ab, something like. If you can do the you know, the second order factoring, you should be good for my class, because I'm not going to ask you to do the cubic factoring or something. It's way too hard. You are a biotech student. You do not need to know something harder. If you need more cubic factoring, just open internet or open the table. Why don't you have to do something hard in this class? Well, we're gonna just do the simple one, only the second order factoring. Does it make sense? All you need to know is this. Well, if you can factoring to the second order, fine. Don't throw harder problem to me like, oh, Ajahn, can you do this one? Like the fifth order factoring is ridiculous. We're gonna do something simple. We learned the concept. We didn't learn algebra here. We are not supposed to learn algebra here. We learned the concept of limits. Okay, so this is a 2 here. Good, fine, makes sense. So factoring is the first one that you should keep in mind, that you can do it every time when you see 0 over 0. Check first if you can do factoring. Well, if factoring does not work, let's go to the conjugate. Well, how do you know that you're going to use the conjugate, everyone? So the trick is that if you see square root sign, it suggests that maybe you should do conjugate. Because if you see square root a minus square root b, well, this gonna be not okay to do the factoring, because square root a minus square root b gonna be the thing that is very hard to factoring. What we should do is we're gonna multiply by its conjugate. Well, you're gonna see it in next slide. Okay, let's look at example 4. Well, we're gonna look at the example that you should use the conjugate to solve this one. So let's evaluate limit where x, y go to 4, 5 of this function. Well, again, everyone take a step back. When you look at the limit problem, for the first time, you need to try to plug in number first. If it is not 0 over 0, you are good to go. You do not need to use factoring or conjugating it at all. All you need to do is, let's try to plug in first. Well, let's think. Well, let me try square root 4 plus 5 minus 3, square root 3. On the denominator, you have 4 plus 5 minus 9. This is square root 9 plus 3. This is 0. Oh no, this is 0 over 0 again. So which means you cannot plug in. Well, you know, if I change this thing to number 8, for example, and then you get 8, and then you get 1, 0 over 1, this is 0. Well, you're done with this question. You do not need to do anything. Does it make sense? No need to do conjugate or no need to do factoring at all, because if it is computable, fine. But here, we got into the trap. So it's 0 over 0 again. It's 0, 0, it's 0 over 0 again. So it's indeterminate form. So we need to do conjugate or factoring for this class, conjugate or factoring. However, you can see that square root x plus y scare you, right? You feel like you don't want to factor this one. Well, if I were you, I'm not going to factor for sure, because how do I factor this thing? It seems like it's impossible to do it. Because factor gonna be good when you have square or something that you can pull out, but it seems like you don't have anything to pull out here. So my suggestion is we're gonna multiply by its conjugate. Oh, let's multiply by its conjugate. So the conjugate of square root x plus y minus 3 gonna be square root x plus y plus 3. Sounds good? This term, I swap the sign so I get its conjugate. So I hope that if I multiply conjugate, the thing on the numerator gonna be in the nice form, and I can, yes, I can compute it. Well, when you multiply square root x plus y plus 3 on the top, you also need to multiply square root x plus y plus 3 on the bottom as well. This is because you want to keep everything, balanced. So you need to multiply by something that is number 1, because this term multiply 1 going to be the same thing. So if you multiply the top, you should keep it in the bottom too, because you want to balance it. Every time you're going to do this when you see the when you want to use the conjugate technique. So, well, let's simplify. This is limit x, y go to 4, 5. And then here we go. So on the top one, well, you can see this is going to be a minus b times a plus b. So it's going to be a squared, which is x plus y. And then it's going to be minus b squared, which is 9. Well, I hope this is not too fast for you. So I multiply the term that I highlight in green and highlight in yellow. I multiply them together, so I get this term. Okay, and in the bottom, I keep everything clean, so I just copy everything from the question. And then you can see now, oh, wow, x plus y minus 9, they're gonna cancel. They cancel out, right? X plus y minus 9 on the top and bottom. These are the same thing, so they cancel out. So which gonna give you limit x, y go to 4, 5 of 1 on the top minus over square root x plus y plus 3. And this is 1 over square root 4 plus 5 plus 3. Well, you do not need the conjugate now here, because here you get rid of the problem 0 over 0 already. So you're ready to plug in. When you plug in, this is going to be 1, 6. And that is your answer. Well, very simple, right? Very simple, right? Well, again, if you feel like you are not comfortable with example 3 and 4, well, we're gonna have more practice problem for you. But keep in mind, every time when you do the limit computation question, well, again, one more time, if you can plug in this thing, it is computable, good, answer that one. If it is 0 over 0, well, think about factoring or conjugate. Well, if you see square here or something that you can pull out, maybe conjugate, maybe factoring gonna be the best way to do it. But if you see square root sign here, maybe the conjugate one gonna be the one that you should try. And hopefully it's cancel out, and then you can compute limits. This is the concept that I'm gonna tell you for the first one, how to compute limit. Sounds good? Well, before we head to the next topic, so at the end of this handout, you're gonna see the practice problem here. This is the one that you can practice. Well, you can try, when you are at home and you feel like, oh, let's try to practice for the final exam or something. Let's do example 13.1. For example, you try to plug in. If it is computable, good. If it is 0 over 0, maybe you're gonna need to factor or conjugate. Let's see. Here, square root sign gonna suggest you to do the conjugate. For example, well, if you can do all this problem, this should be good. Well, I also have the solution of this problem as a video clip, because because last year I record the solution for each example in the video clip already, so I can give it to you and you can look at the solution after you did it. Make sense? So this is a practice problem. Keep in mind, practice problem gonna be at the end of the handout. You can always practice your skill over there, because they're gonna be the similar question to practice problem on the exam. And if you do that, you sharp your skill and should be good. All right. Well, this is the end for the first part of computing limit using 0 over 0 and conjugate. Any question from students? Anyone want to ask questions? Are you still listening to me? Good, everyone? Good now. Anyone have any question? Good. Okay, good. So thank you everyone for listening to me and yeah, show your attention here, because I hope that, well, I do respect your time, and if you will participate and be with me a lot, so I remember your name, and that should be good for you to pass the class. And I do respect people who attend class and participate, because I memorize the name, I monitor all the time, and yeah, so I know you took so much time or so much effort to do this, so I'm not going to fail you for sure, and I will keep your grade good as well if you attend class a lot. Okay. Well, but 50% depend on me, but 50% depend on Ajahn Thirapong. So I don't know if you do, if you did pretty bad or pretty good on the first half, but the second half you should be good. Well, okay, some of you asked about the book, so I'm gonna talk about the book later. So, well, there is a book. I think we use a Stewart book, James Stewart book. So you can look at one chapter in James Stewart book that it's gonna refer to this content. But well, I'm gonna show it later after break. Okay. Well, that's the question from Mila, I think. Well, let's hold on. After break, I'm gonna come back and show you where you should read if you want to read the book, the textbooks. Okay, good. All right, next we're gonna look at the thing that I mentioned last time. Well, let's talk about this thing for 20 minutes more, and then I'll give you a break, okay, everyone? So what are the differences compared to one variable case? Well, I told you last time that the thing that is very, very interesting, and it's gonna be different from the one-dimensional case is, let's talk about that. So in one-dimensional case, you used to have the left hand limit and right hand limit, as I told you last time. But in two dimension, it's gonna be totally different, because now you are working on the plane XY, and the point that you are trying to get the limit approach to, it's gonna be AB, which means you can have so many line approach it. Well, this thing is very interesting, because you know what, we have a theorem in math, or you can call it remark or something. Well, theorem number one is, if the limit of fxy exists, if you know that the limit xy fxy where xy go to ab exists, if you know that it does exist, so, and it is L, and you know that the value that you get is L, then what happened is fxy gonna go to L on all smooth curve. Okay, which means if you know that the limit is equal to L, then for any line that approach AB, the limit gonna be L as well. It does make sense. Well, don't be scared about the word smooth curve. Well, the curve that we learn in this class or in the basic calculus gonna be all smooth curve. Well, there's gonna be some type of curve that is not smooth, something like the stock market or something that we don't call it smooth curve, because it's so hard to get the equation. It's so unpredictable to have the equation. Those type of curve we don't call smooth curve, but everything that we learn in this class is going to be smooth curve, so that will be fine for you, because the curve that we learn, like the line, the parabola, everything that we learn is going to be, we call it smooth curve, because it's easy to get the equation and pattern of that curve. So, well, number one is not that interesting, but number two, this is interesting, because we know that if the limit exists, every line you're going to get the same limit. Well, this means if you find any two lines that give you the different limits, then the limit does not exist. Well, this is very important. Well, start here. If fxy has two different limits as xy go to AB, if you feel like, oh, you can find two smooth curve that you're gonna get two different limits, then the limit does not exist. X, Y, go to A, B here, does not exist. We're gonna look at the, we're gonna look at the example in few minutes, but hopefully you understand what I just said, that, well, if you find two lines here that give you different limits, the limit shouldn't be exist, because if it exists, every line gonna give you the same limit. This is the same logic as, well, I am not sure if you learn mathematical logic in your high school, but if you used to learn mathematical logic, you're gonna see that, well, the statement P imply Q gonna be the same statement with not P, not Q imply not P. These are the equivalent thing, because if you want to say that if it lands, the dog will bark. This is the same thing as if the dog does not bark, it will not rain. Well, these are equivalent statement in logic. So it means, you know, if you know that the limit exists, well, it must be the case that limit on every line must be the same. Well, in other words, this is my P, this is my Q. Well, this is the same thing with not Q imply not P. So which means if you find two different limits that they are different, so it's gonna, we can conclude that the limit does not exist. Okay, so let's take a look at example and you will understand more after you see example. Okay, so before example, here this is example. So fxy is the case that the limit exists, because every line when you go here, as we talked last time, you can see that the value of the fxy approach number 1. So which means at the end limit gonna be 1, and no matter what you come on this line, any line, so it's gonna be limit gonna be 1. But gxy, this is the function that the limit does not exist when the point approach 0, 0, because at some line you get 1, some line you get -1. For this case, if you feel like you can find two lines that the limit they are different, so you're gonna conclude that the limit does not exist. This is the way we conclude that the limit does not exist. Okay, well, hopefully example 5 and 6 gonna help you. Okay, so let's try to look at example 5 first together. Well, we want to show that this given limit does not exist. Well, this means when you see the question like this, it forces you to show that it does not exist, which means they want you to pick two lines that give you different limits, so it does not exist. So let's take a look at that. Well, see, this is your first example on showing that the limit does not exist. So I'm going to show the full solution for you. Limit x, y go to 0, 0. Well, x plus 2y over x minus 2y. So what you need to observe first is xy go to 0, 0, which means if you draw the plane here, the point that you are interested in is 0, 0. This is the point that you are interested in, okay? So you could have so many lines that you know, approach 0, 0. The first and very easy line is this line. You can come to 0, 0 on this line. This is along y equal to 0. You can do that. You can do this one as well, come from the top. This is going to be along the line x equal to 0. That's okay too. And you can come to the point 0, 0 on this line, and that will be along the line y equal to x. You could have any line that approach 0, 0. You can pick anything you want. For those of you who want to challenge yourself, pick something hard, you can come to the point here by using the parabola line. And you say, this is going to come along with the line y equal to -x squared. Well, fine, you can do it if you want. But to keep it simple, so we're going to pick the easy line first, y equal to 0. So we're going to compute this limit. Take a look at my notation on y equal to 0. So this is our first line. So we're going to pick y equal to 0. We're going to look at the limit where it's come to the 0, 0, 0 y on along the line y equal to 0, which means you can plug in y equal to 0 now because you're going to choose y equal to 0. So it's going to be limit x, y go to 0, 0. Well, this time you force it to be on y equal to 0. That means you can plug in y equal to 0. This is x plus 2 times 0. This is x minus 2 times 0. Y equal to 0 now because you force it that y equal to 0. Here, you're going to get, oh, good. That's going to give you the limit x, y go to 0, 0 on y equal to 0. And that is x over x. Oh, okay, you get 1. Well, the limit when you come from this line is 1. Okay, let's try to do different one. Let's try to do the second line here. Okay, let's try to do something different. Hopefully, after you pick the second one, you're gonna get different limits. So let's take y equal to x then. Well, I mean, you could have different solution because I mean, some of you are gonna pick x equal to 0, fine. But let's suppose that I wanna challenge myself. I pick something harder than x equal to 0. I pick y equal to x. Okay. So what happened is, well, this time I can plug in y equal to x or x equal to y, the same thing, into the function. So which means I can do x plus 2x. Well, good. Well, on the top, well, I plug in y equal to x because now I'm looking at the limit from this line. Make sense? And that will be x minus 2 times x as well. So this on the top, well, let me simplify it here. You're going to get 3x, right? Here, you're going to get negative x and x cancel out. So which means, oh, the limit at the end, you're going to get negative 3. Does it make sense here? Well, which means you have limit on y equal to 0 is 1. Limit on y equal to x is negative 3. Well, it's going to be the same case that when it's come here, you get negative 3. When it's come here, you get 1. So you have two lines already that it gives you different limits. So which means the limit does not exist because the limit of the function, let's say fxy here. Let's copy the question. X plus 2y minus x over x minus 2y, xy go to 0, 0 on y equal to 0, you get 1. This is not equal to negative 3, which is going to be another limit that you compute with the same function, but you compute on different line. Well, you concluded that they're not equal to each other. Because of this thing, we conclude that the limit does not exist. How do you feel? Understand it? So this is the way we we conclude that the limit does not exist. You can see that the technique is draw the picture first, so you can see what line you're gonna pick. You can pick any line you want as long as it approaches 0, 0, 0, the point that you are interested in. Well, some of you are gonna pick y equal to 0. You can get 1 here. Well, if you pick x equal to 0, the limit here gonna be negative 1. You can see that you can pick any line you want, but as long as you find two different ones, you can conclude that the limit does not exist. Sounds good? All right, one more example and then we have a break, okay? All right, example 6, show that limit of xy go to 0, 0 here, x square y, x to the 4th power plus y square does not exist. Oh, first of all, before you use this technique, well, you should keep in mind that when you plug in 0, 0, and then you're gonna get 0 over 0, that is why you cannot just plug in. You see that part? Because before we learn that when you have limit, you can plug in x, y first. Well, but here, if you plug in x, y, x to be 0, y to be 0 inside there, so you're gonna get 0 over 0. And the factoring and conjugate will not work on this question. That is why the question asks you to show that the limit does not exist. Okay. First of all, well, because we know the goal already that we're gonna show that the limit does not exist. So we're gonna pick two different lines. Okay, we're gonna pick two different lines. Anyone answer me in the chat which line you wanna try? Well, we're gonna do this example together before the break. So let's start back. Let's draw the picture first. We have 0, 0 here. So you can pick any line that approach 0, 0. So which one is the first line that you want to pick? Anyone want to answer me in the chat? There's nothing right or wrong. Okay. You can type in public. Okay. You don't have to type in direct message because if you type public, it's gonna save it to my computer automatically, and I know you participate. Okay. The first one, I have Jantanipa. She wanna pick y equal to x. Good. Well, let's do y equal to x, everyone. Limit x, y go to 0, 0 on y equal to x. This is what you wanna do. And x square y over x to the fourth power minus y square here. So you're gonna plug in everything. So let's do limit x, y go to 0, 0 on y equal to x. So this means x squared times x, okay? And then x to the fourth power plus x squared. Is it good? So on the top, you're gonna get x cubed. Let's think about that. On the bottom, okay. This sounds reasonable. Let's see if you can do it. Limit x, y go to 0, 0 on y equal to x. And then you're gonna have x cubed over x to the fourth power plus x squared. Well, which you can pull out x squared, right? So you can feel like, okay, I have x squared times x on the top. The bottom, you pull out x squared, so you can cancel out. You get x squared plus 1. Sounds good. And then you cancel x squared out. Here you're gonna have just, okay, if I plug in x equal to 0, because x, y still go to 0, 0, okay? Up to this point, you have x over x squared plus 1. Well, you can have x, y go to 0, 0 as well. So you're gonna get 0 squared plus 1, and that is 0. Good, yeah, this is the first line, 0. Which means, Jantanipa, right? I'm not sure I pronounce your name correct, but well, we pick the line y equal to x already. It's 0. Well, now it's everyone's turn that we need to pick the different one, and the limit that we get, if we get different things than 0, that will be our answer. Here, most of you are gonna say, let's pick x equal to 0 and y equal to 0. So, right, because in the chat, everyone say x equal to 0 or y equal to 0. That is most of your answer here. So let's do that. Well, if I pick x equal to 0, what happened? So I'm gonna copy this thing and paste. Okay, come in different color, please. And then, well, let's suppose that I change this thing, everyone. To take a look at the green pen now. I'm gonna change it to x equal to 0 as suggested. Okay. The problem is if you choose x equal to 0 here, you can plug in x equal to 0 now. 0 squared times y over 0 to the fourth power plus y squared. It's 0 as well. You see that on the top one, you get numerator 0. The bottom one, you get 0 to the fourth plus y squared, which you still get y squared here. It's 0 over y squared, it's 0. This line will not work. This is one problem that you see. You see, people, you could pick different line and you get the same limit. Does not work. So you still need to try to find some line that it's going to give you different limits. Well, let's look at the chat. I think more people answer. Okay, let's try the answer. Next one, Tayida, right? Tayida, I'm sorry if I pronounce your name wrong. Tayida, y equal to x squared. Okay, let's try her approach. Well, let's see if it works. Because she said that she want to try y equal to x squared. Still good to use because it passed 0, 0. Okay, let's try y equal to x squared. And see, this is going to be a beautiful solution or not. So on y equal to x squared, people, here is x squared, and then oh, you use y equal to x squared. Sounds good to me. I love it. And then on the bottom here, I have x to the fourth power, and then here you have y equal to x squared, and then you square it. Seem like we have a light at the end of the cave, right? Because it seems like it can do something. So on the top you have x to the fourth power, and then here you have x to the fourth power plus x to the fourth power. Wow, this is so good, because if you pick y equal to x squared, so on the top you have x to the fourth power, on the bottom this thing is also 2 times x to the fourth power. It means her answer is actually perfect for this question, because you're gonna cancel x to the fourth power out, and then you get 1/2. Beautiful. So we have 2 different limits. So the limit doesn't exist. Any question on this one? Well, if you feel like you want to challenge yourself, you can find another line that the limit is different, right? But you know, for this question, most line gonna give you 0. So it's hard to find a line that fit perfectly, give you different limits. Well, I think that Taida, she has a brilliant idea, because, well, let's see everyone, if you want to have that trick, let's look at the behavior of the denominator here. What you can observe is you have x to the fourth power here plus y squared here. If you pick y equal to x squared, you're gonna balance the power here to be 4. And this is the key idea, that she picked y equal to x squared because she want to group this thing up to be x to the fourth power, and it cancel out. The same thing when you do the question on the practice problem. Something like that. How would you balance it or something? Well, if you want to show that the limit doesn't exist, yeah, it's gonna be the challenge one. I will not steal your practice problem, but well, I will let you do this practice problem by yourself and check the solution with my video clip on the YouTube channel. But well, you can observe, well, you learn a little bit more today that, hey, there's gonna be a trick here that you need to pick different lines, and then you get different limits, and you can conclude that limit that exists. This is an art that you need to pick something that it works, you know. And how do you know this thing? It's our experience. You know, when I was a kid like you, I also had a hard time to pick the line that I want, but experience gonna help you. If you practice more, you do more problem, you're gonna know, oh, we have seen this thing before. Well, this should be a technique, standard technique. So you learn each day, you learn more and more. So it's gonna sharp your skill, and at the end, when you see this type of problem again, you're gonna feel like, oh, I know how to do this. You have to pick something that balance the denominator or something. Well, let's suppose I change this thing to x to the 6 and y squared here. Maybe plus y squared. The chance that you should use is going to be y equal to x cubed. Because you know that if you pick y equal to x cubed, it's going to balance here. And maybe the top one going to be different denominator already or something. Sounds good? All right, we're going to have, I think, 15-minute break. Okay, everyone. Come back at 11:10. So we're gonna stop the class on the first hour here. Once we come back at 11:10, we're gonna look at another theorem, and that is the last one for today. So after we come back at 11:10, we're gonna learn about half an hour more, I guess, and then we're gonna stop the class. Okay, because we need to learn one more technique, which is called the squeezing theorem. Well, the thing that you learn in Cal 1 still works in Cal 2, called squeezing theorem. So we're gonna learn that after the break, but we're gonna stop it here before the break. So everyone, 15-minute break, 10:55 to 11:10. We come back at 11:10. All right, sounds good. All right, let's have a break. We'll come back at 11:10, everyone. Well, oh, sorry, let me that exist. My tea is bad. Okay, good. All right, break up. So let's talk about this theorem together. Okay, ready? Let me open my notes. Where's my note? Oh, where's my note? 1 second. Where do I keep it? Okay, I found it. All right, so another theorem that you can use is the, I call this thing two-dimensional squeezing theorem. But you know, in the book, they didn't say that it is squeezing theorem, but I love to call it squeezing theorem because it matches with the thing that you learn in Cal 1. So theorem. This is another way to compute the limits. So what I call this thing two-dimensional squeezing theorem. Squeezing theorem. You know, in Cal 1, you have something called squeezing theorem or sandwich theorem, the same thing. So the statement is if f and g, if you have two functions, are functions of two variables, you have two functions f and g, and you meet two conditions. So number one is, you know that function f, it's bounded by some number m. Well, you know that there's gonna be some number m that you know is the upper limit of absolute f. Well, this is in math, this is called f bounded by m. You know, m must be a positive number for sure. And the second one, and two, if you know that the limit of function g gonna go to 0 where x, y go to a, b. Well, if you know these conditions, well, if these conditions are met, so then what you can conclude is limit of fxy times gxy gonna be 0, completely 0, where xy go to ab. This is actually amazing in terms of, well, you know, when you see limit for the first time, you're trying to plug in number and you hope that it's gonna give you something good that is not equal to 0 over 0, right? And if you face 0 over 0, you're gonna feel like, oh, I'm gonna do factoring, I'm gonna do conjugate. Well, next step after factoring and conjugate do not work, what would you do? You're gonna say, oh, maybe limit does not exist. So you're gonna pick different lines or different curve, and then you're trying to say that limit does not exist by finding two different curves that give you different limits. But what if you're trying to do that and you always get 0? Let's suppose that this supposed to be different function and you keep picking the line and you always get 0, 0, 0, 0, 0, 0, 0, and you feel like, oh, I'm about to give up because every time I pick every line, it's always give me 0. Well, you may have a question in your mind, is it actually 0? Well, if you want to show that the limit is 0, this is one way to do it. So you have two functions. One function is bounded by m. Another function is its limit is 0. Then you can conclude that the limit of the product it's indeed 0. This is actually the very, very good result. Well, I call this thing squeezing theorem because you see that when you have absolute fxy less than or equal to m, it means you're gonna have fxy it's bounded between negative m and m. And if you multiply fxy by g, well, it means you multiply through the, you know, all the inequality here. So you have to multiply both sides by gxy as well. And you know, if you want to compute the limit of the middle term here, but you know that the limit on the right hand side is 0 because limit of g is 0. And you know that limit of the left hand side is also 0. Well, it's gonna squeeze, or it's gonna be, you know, by sandwich theorem, it's gonna squeeze that the term in the middle, the limit must be 0 as well. This is why we call this thing two-dimensional squeezing theorem. Well, we're gonna show you the example how to use it. Two examples in few minutes, but keep in mind that this is not easy to use. Well, the reason that it is not easy because you need to show these two conditions, and the hard one is number one here, because it is not easy sometimes to show that f, the absolute, gonna bounded by m, but there are some techniques. So let's look at that. So example 7 and 8. Okay, I think two examples and then we can stop the class. Because we're going to come back with the continuity on next Monday. All right, so example 7 here. So I want you to evaluate x, y go to 0, 0 of 2x squared y cubed over x squared plus y squared. Let's take a step back first and keep in mind that every time when you see the limit question, first of all, you plug in, right? If I try to plug in 0, it's going to be 0 over 0. Well, you can see clearly that if you plug in 0, 0, 0, 0, well, it's going to be all zeros, and that means 0 over 0. Yeah, so plugging in does not work. 0 over 0, would you try to do conjugate or factoring? Well, I don't see square root anywhere, so I don't feel like conjugate is a good way to do it, so I'm not going to do it. And also factoring, I have no way to factor this thing. Well, if it is x squared plus y squared, I know how to factor it because it's going to be x plus y, x minus y. But this is going to get stuck for sure. I don't know how to factor it. X squared plus y squared, it's ridiculous. It's no way to factor it. So no plugging in, no factoring, no conjugation. Well, the next way you should think of is maybe the limit does not exist. Maybe I should pick different lines. Well, let's do the scratch one. If I pick x equal to 0, what happened? So it's going to be 2 times 0 square y cubed over 0 square plus y square. And then, okay, on the top you get 0. The bottom you get y square. Okay, if I pick the line x equal to 0, the limit going to be 0 now. And then if I pick y equal to 0, whoops, what happened? So it's going to be 2x squared, 0 cubed, and then x squared plus 0 squared. Okay, this is going to give you 0 over x squared. Oh, wow, the limit going to be 0 as well. Shouldn't be so bad over there. So x equal to y. Well, let's try the easy one. It's going to be 2x squared, x cubed over x squared plus x squared here. Okay, on the top I get to x to the 5th power and then x to the 4th power. Okay, cancel out. You get 2x. But this is limit x, y go to 0, 0. So it's actually 0. Tired. What should we do? It's like all.
So, John, I don't think x squared plus x squared is x to the 4th power.
Okay, sorry, 2x squared. 2x squared. Thank you, Ego. Well, you're smarter than me. I'm speaking too fast. Thank you for that declaration. So this is 2x squared. So it's x cubed. Yeah, it's also 0. Well, thank you. Well, what else? You probably think that, yeah, maybe we can try y equal to x squared, or we try y equal to x cubed, or you can try some all the functions that you try that pass 0, 0. Well, believe me, it's gonna give you all 0. And you're gonna keep trying, and it's actually always give you 0. And if you feel that way, you feel like maybe the limit is actually 0. So if you get to this situation, well, let's try to show that the limit is actually 0 by using the squeezing theorem. Okay, this is the last technique that we're going to learn for this class. Well, okay, so to show that the limit is actually 0, so let's do it. So we're going to split this thing to x squared y cubed over x squared plus y squared. We're going to split it into parts, 2 brackets. The first one, I'm going to call it f. The second one, I'm going to call it g. Well, your task is you're going to split this one into 2 in the product of f and g. What you need is, after you split, you want to show that fxy take absolute, gonna less than or equal to some number. And you want to get the goal that the limit of function g must be 0. Okay, this is your goal. if you can show that number 1, number 2, they are done, then you can conclude that the limit is equal to 0. So what should I do? So the trick here, I'm gonna tell you the trick. You should take all the denominator with f. You're gonna see in a minute why. So I'm gonna take x squared plus y squared to f here. Well, on the top one, I'm gonna say that, okay, let's take x squared here. And the remaining term 2y cube, kick it to g. So let's see what happened. So fxy here, if you pick it to be x squared over x squared plus y squared, so what you get is x squared over x squared plus y squared. Okay, and this thing gonna be less than or equal to x squared plus y squared over x squared plus y squared. You may have a question why. This is because you add y squared to the top. Well, you add some positive thing to the top. This top thing gonna be always greater than or equal to this thing, always, right? Because you add y squared on the top. You didn't touch anything on the denominator, so denominator gonna be the same, but the top one you add this term, so this term is heavier than this one. So this one must be bigger than that. And on the right hand side, you can cancel out, you get 1. Which means you can show that absolute fxy here gonna be less than or equal to 1. So we add y squared because we wanna have this thing to cancel out and get 1. This is the technique that when you see it for the first time, of course, you're gonna have a question why Ajahn add y squared here. This is just a trick and a technique we do it. Because we add them because we want the right hand side here to cancel out and get 1. Otherwise, you don't know how to bound this number. Does it make sense? Well, you can add any positive thing here on the right hand side and use the less than or equal sign here. Because you add a positive thing, the top one gonna be bigger for sure. I told you, I'm gonna tell you here, this is the key step. The hardest step for this content, because usually students are struggling with this step because they don't know how to bound it here. And this is the technique that, well, you're gonna get better after you see more example. But x squared less than x squared plus y squared because I add y squared here. Technically, I can add any term that is positive. You can add it because think of you add something more, the positive thing, so it's gonna be heavier for sure on that side. Well, and number 2 is easy now because if you keep g over there, so it's gonna be 2y cubed, and that will, once you plug in 0, it's gonna be 0. So technically, number 2 is always easy. Number 1 is gonna be the hard one because you need to bound it with a number. So number 1 clear, number 2 clear. So by two-dimensional squeezing theorem, limit of these two functions f and g multiplied together, where x, y go to 0, 0. This is actually 0. Well, which means, limit f and g is the one that you want to compute, 2x squared y cubed over x squared plus y squared, okay? And that is the solution for this problem. Keep in mind that one thing, that's more than one solution. You don't have to follow me. Some of you are gonna say, Ajahn, what if I split fxy and gfy to be different one compared to Ajahn? Am I correct? The answer is possible. It is possibly that it is possible that you're gonna get different split f and g, and it is also correct. If you move number 2 to this side, it's still okay because you're gonna have 2 here. You're gonna have 2 here, and it's fine as long as you bound with any number. Well, you can put 2 here as well, or you can pick this to be y squared, and then you keep 2x squared y with g. It's okay too. any split that you get these two conditions, that will be fine. Okay, that will be fine. Does it make sense? Well, again, the trick is here. Well, when you do the inequality, this is an inequality. That is why it works. It is not equal. It is an inequality. So as long as you add some term and you make sure that the right hand side you have something heavier than the left hand side, that would be fine. Okay, so I hope I answered the question that some of you asked me in the chat. You know, if you still don't understand, so well, let's review by yourself again, and maybe if you take some time off to study, and if you feel like this is still your problem, talk to me again, so I can try to explain it in the easier way. But you know, this is a trick. This is the hard one because this is a trick. That's why it is hard, and well, you need experience. You need to gain more experience to understand, to use this trick again and again and again. Okay, so well, let's talk about the last example. The last example for today, we're gonna look at example 8. So the same technique as before. We're gonna try to apply the squeeze theorem, but this time, square root sign gonna make us more gonna make it harder to bound it in the F. Okay, well, 1 second, I read the question in the chat. So when you ask question in the chat, you can ask in public, okay? So everyone can see that question too, because no question is stupid. Everyone, there gonna be a lot of people have the same question with you, but they are afraid to ask. So if you ask, you help people too, because your friend, sometimes they are shy, they don't want to ask. You know, if you ask, you help your friend too. And I'm gonna answer that question too. Well, let me read the chat first. We can add or subtract or multiply relation. So number 1. Well, I do not understand that question who asked me in the direct message that we can add or subtract or something. Well, maybe ask it again, so be more clear. So sorry, I do not understand. Okay, well, I'll come back to questions after example 8. Okay, let's finish this one first. So example 8, let's try to evaluate this limit. So again, well, before you use the squeezing theorem, you should make sure first that the limit is not computable. So you plug in 0 already. It's always 0 over 0. You don't want to use conjugate, or you don't want to use factoring. So some of you are going to say, Ajahn, why don't you use conjugate here? It will not work. You could try. You could try. This conjugate will not work. This is not actually the part that you're going to use conjugate, because the square root side is all x and y here. If it is square root this plus square root this, that could be conjugate. But this thing is not always good. I mean, this is not good to do conjugate. Factoring is not going to be good for this question as well. No plug in, no conjugate, no factoring. If you're trying to pick the line, try x equal to 0, y equal to 0, x equal to y. Any basic line gonna give you all 0. Well, at the end, it's gonna force you. Well, before you use the squeezing theorem, well, you should try other methods already, and well, you spend maybe 2 or 3 minutes to think of other methods, and you feel like, hey, at the end, I always get the limit equal to 0. So it's gonna come to this technique. Okay. All right. So let's do this thing. So I have 3xy over square root 3x squared plus y squared. What should I do? I need to split this thing to f and g. Well, same technique, nah? F and g. Well, what I need is, I need that my function f, when I bound it, I need to get some number here that bound it. That is what I want. Number 2 is I need limit of function g equal to 0. Well, as I told you in the previous example, that your g here, you do not need to worry about g a lot, because so that the limit is equal to 0 is easy, because well, at the end, if you kick x to that, or if you kick y to that, it's gonna be zero easily anyway. So the part that you're gonna take a lot of effort to do it, it's gonna be the part one. So as I suggest on my trick, I always put the denominator on the f part, and you should too, because this is going to give you more more room to work with the bound. You know what I mean? Just like if you put this to be a fraction, it's going to be easier to bound it with some number. So I'm going to keep square root 3x squared plus y squared on the f part. Okay, let's do that. Well, let's build a Lego here. So let's suppose that at the end I want number one here. At the end I want number one to be the bound. Number one is going to be square root 3x squared plus y squared, right? And then square root 3x squared plus y squared. If you have that one, it's gonna cancel out to one. Everyone know this because they are the same thing. So how do I bound it? So this term, I guarantee that it's going to be greater than or equal to square root. Well, in the bottom, I didn't touch anything, but this term, I can guarantee that this term on the right hand side, it's gonna be bigger than square root y squared. Would you agree? Because you compare it. Look, the one that I highlight in yellow, y squared, and this is 3x squared plus y squared. This term on the right hand side gonna be bigger than this for sure, because from left to right, you add 3x squared. This is a positive thing. You add a positive thing, this side gonna be heavier. Well, this inequality valid because I add the big thing on the right hand side. And also, okay, if I take square root of y squared, it's y, which means I should keep y here. 3x, you go that way. Does it make sense? This is one way we, I don't know how to explain it. It's our experience. If you do this type of question again and again, you're gonna gain more experience, and you're gonna see this type of question. Like, I don't know, you may have a question that Ajahn, why when Ajahn did it so quick and easy? It is because I see this type of problem more than 100 times, so I know the technique. But for you, it's okay if you feel like this is hard. This is your first time. Everyone, when I was a kid like you, I had a hard time too. This is, and the technique here, as I told you again, trying to use number one as your bound is the best way to do it. And maybe you start with that one, like I show you, and trying to see that, can you say that the top is greater than or something with this thing? And once you have this thing that is smaller than the smaller now, if it reduces to something, okay, let's just keep one here. Done. Which there are more than one solution. If you feel like you want this thing, and Ajahn, can I do greater than square root x squared? It's okay too, right? Some of you gonna say that, can I use this thing? It is okay, good. Because this is also correct. Because from x squared here, it's less than on the right hand side for sure, because you add 2x squared plus y squared. You add a positive number, so it's gonna be less than or equal to, and then you can keep x here. And then you're gonna use x here, and this is gonna be 3y. Well, different f and g also works. And then here it's gonna be 3x. This is you plug in 3 and 0, you get 0. Good. Okay, now I'm done. By two-dimensional squeezing theorem. So the limit is actually 0. Limit of the given term here is indeed 0. Okay. Yeah, we are done with this question. Sounds good. Well, this is all the content that you learned today. Okay, makes sense? All right, so again, if you want to practice, there must there are some good example in the book. In the Stewart book, you have that one, and also you also have practice problem here, which you can see that this question 14 show the limit does not exist. This one you have to pick the line for sure. The continuous one we're gonna come back and learn on Monday, nah? And because I don't want to be rushed on the content, so better for you to take a rest, and then we're gonna see you next week with the continuity content. And here, evaluate the following limits. If the limit does not exist, explain why. So you can see this type of question. You can try to pick the line first. If it works, yeah, it works. So you're gonna conclude that the limit does not exist. But if it does not work, maybe you need to split it into F and G and use the squeezing theorem. This one too, F and G. Look, if you cannot pick the line, this one too. If you cannot pick the line, you can see that. And when you pick F and G, you should keep this thing, the denominator, in the F part, you know, and trying to start from the bound on the F and trying to see what you should carry with you, the F1. Maybe you're gonna carry only x squared, this thing, this part to the F1. Everything else you kick to the G part and show that the limit is equal to 0. Yeah. Well, let's try. Yeah, you know, if you have time, do all of them. So the solution is, I will post solution later. Well, I will use a clip from last year, the solution. Okay. All right. So we learned a lot today, nah? Actually, since 10 a.m., this is a 2-hour class. So we actually learned a lot today. So hopefully you absorb the technique how to compute limits from today's class. Give the thumbs up if you feel like you are okay with the content or the reaction, you know. Sounds good. All right. Some of you did pretty good. Okay. All right. So, well, before you leave, please sign your name in the chat, and then we're gonna end the class today. Sign your name in the chat today, so I know you are in for today,นะครับ. And then I will see you again on Monday. So sign your name in the chat, please. So public chat, okay? So it's saved to my computer automatically. Okay, thank you everyone. I will see you again next Monday, nah? Have a good weekend,นะครับ, everyone.